have any questions, I will answer.
Thank you. Thank you for your presentation. And there is any question from the audience? Just a quick one, please.
Thank you. Yes, thank you very much for interesting talk and very clearly presented. Thank you. Can you tell us a little bit more about exactly how it fails physically? Because I mean, as you said, I guess it's the fibers that are actually breaking, yeah? And does it fail more like in the center where the loading point is, or all along, or what happens?
Yeah, it fails about the actuator in the middle. That's one thing, and also it usually cracks either on the rubber, but usually on the interface between the rubber and the reinforcement. So it's
okay, more the interface than the actual
yes.
fibers. Okay,
we will analyze it later on the microscope and also on the X-ray, so we'll have the exact results. But like I analysis told me that it's on the interface.
Thank you. Thank you.
Thank you again.
Thank you.
So we can proceed with the second presentation that is going to be given by Tadeusz Łagoda, and it is about aluminous alloy 606 series after cyclic and impact bending.
Pointers, yes. Mr. Chairman, ladies and gentlemen, also is our presentation is from Opole University of Technology, and also there are two co-authors from the body company, and the Sławomir Małys is PhD student. This is part of his PhD study. As the chairman told, the type is aluminum alloys, the 6xx after cyclic impact bending. Okay. Also have problem? Yes. Okay. The scope of presentation, introduction, some words about materials, about experiment, result and discussion, impact step of breaking work, fractographic analysis, surface analysis, and on the end, as normally, some conclusions. This paper presents the results of fatigue and impact bending tests with a primary focus of the surface topography of the resulting fractures. 3 aluminum alloys were used for this study, 660C and T6 and T64, and 6063 with T6 heat treatment condition. These aluminum alloys are used for made windows and doors in the trains. Because the trains now are made not from the steel, but from the aluminum, the base is aluminum, big frequency, time, so problem which is very big, so it's necessary to analyze aluminum. Because of steel, you know more, in aluminum alloys less. So it's necessary to analyze this material. So this material 660 and 6063 are very close. You may see that the magnesium, sorry. Oh, okay, the more magnesium is in the 6063, a little, but it's influence of fatigue and static strength and also impact. So in the first, it was necessary to see how it looks the static. We see that the higher strength is possible for material 6060 in the T6, but the lower is for 6060 T64. But it's a problem because when you make the windows of the doors, we have big deformation. When we use material 6060 T6 in static, the strength is more, but the aluminum sometimes break. So sometimes it's in the factories they use material in this, treatment T64, but the static strength is less. So for the engineer, it's necessary to look what kind of materials to use in the real construction. So it is mechanical properties for these test aluminum alloys is very close to the standard of this material. At first, we did experiment of impact test. It's typical spacement for make impact strength. So here we use two kinds of samples. On the right hand, we have sample photos of samples after impact test. We have used two things, 4 millimeters and 2 millimeters of this material. We see this on the left side, we have fins 4 millimeters. On the right hand, we have fins 2 millimeters. And after calculation, we put here, of course, the mean value of 3 spacement every time, impact strength and braking work. Now we have, of course, only the data of this experiment, 3 materials and 3 thinkers. Here on these photos, we put a fractographic analysis. On the left side is fins right 2 millimeters. On next photos, you may use more how looks the fractography of these materials. This is variant number 1, so this is fixed spacement 4 millimeters, and next for 2 millimeters thin spacement. Also, we may see the fractography. Next, some words about fatigue, because in our university we made many experiments of fatigue, as we see on the first presentation. Also, here we have also no standard for bending and torsion. So we make possibilities to make experiment bending, torsion, and every combination of bending and torsion on this stand proportional with dashing. On the left, okay, on the left down part, we have spacement of this. It is spacement Diabolo in the things it is 10 millimeters. So the spacement is very small. Equipment also is small. Or it is project is at our university, and we make. So we have some problems. In every time you may do some reconstruction, repair, and others. So it's very useful. And you use small energy, very small engine, electrical engine we have on the left. Here is the stand. I hope. I see don't work properly. Sorry, one moment. Here I have seen how it works, but I see it doesn't work. Okay, that doesn't work, unfortunately. So we have put on these photos only experiment or fatigue in bending, because we have impact bending at the first, now fatigue bending. We have 3 characteristics, Baskin equation. So for 3 materials, we see this characteristic. Now it's very difficult to say about what kind of material is better, but you have 3 characteristics with points of materials. But on the next figure, we put 3 Baskin characteristics without point of experiment, but only characteristic. We see that as similar as for static, for material 60C into 6, it has big, you have higher stress. For the material 6060 T64 less, and 6063 T6 in mean. But on the left, we see that is big influence. When we prolongate this characteristic on the right, you may see that after about 10 million cycles, it's nearly the same. For the static, it's nearly, the strength is 2 times more for 60-60, but in fatigue problem, it's no matter what kind of material we use. So for engineer, it's very good information that we may use this material 60-60 T64, the plastic deformation to make, for example, the frame of the window or doors is very useful, but in fatigue, it's no problem. But these trains are project for many, for thousands of kilometers, for minor cycles. So you may use this poorer material, but for engineer, it's more easy to do construction without any break under construction. And here we have fractography of this material after cyclic bending. On the left, you have this material as earlier, 60-60 T64, next 60-60 T6, and next 60-63 T6. So we have see on the every of these photos, fatigue zone, and the middle residual zone in this area, the stress was nearly zero all for fatigue test. And initiation and propagation was from the 2 sides on the upper, and now go to the plate of without stress. So it's typical spacement. Every spacement looks nearly as these 3, as we see on the presentation. And next, we want to see how connection between strength and this impact. On the left side, we have side and the horizontal line, we have ultimately stress, how it influence of impact. So we see that blue circles is the small samples and red squares is for the variant number for small samples. So we have see that is some function that is go down. We have 3 points, so I don't put the function because 3 points put function. We should do such, but we said tendency we see. And next, we should look for fatigue. How is connection in fatigue? On the right hand, we put yield stress divided by modulus of elasticity. So its practice is nearly strain in elastic of this material, multiplied by amplitude from fatigue from 10 power 6 cycles. It's for the steel, it's horizontal. For aluminum, of course, it goes down, down, and down, but it's typical use this number of cycles. So, and the analysis same time for sometimes it's 2 minus. You know, very important. But you see on the horizontal line, you have static and fatigue, but always elasticity and influence on impact strength. Also, you have some tendential function, but it is 3 materials. So in future, you want to use other aluminum alloys and see how it influences. But it's necessary to do experiment. Fatigue experiment we have, it is necessary to do impact. So I think it will be very easy to do this experiment in the future. But no, now we did this directly to the body company, which made windows and doors to the trains. And on the end, conclusion, during explanation, the safety is to use the aluminum alloy 6060 T64. This material has the highest resistance to impact load, regardless of whether the elements are smaller or larger. Such use will result in the highest reliability of the structure in the event of such load. As tensile strength increases, impact strength decreases. For a defined energy, static fatigue, right-hand figure it was, the deformation parameter, and its value increases, impact strength decreases. The material becomes more brittle. Generally, fractographic analysis of two variants of the research sample, smaller and larger, shows that the obtained surface morphology appear similar. You see that was the topography was similar. Fractographic analysis of fracture its sample is subject to the bend fatigue testing related that the 60, T64 and T6 aluminum alloys exhibition similar ductile fracture morphology, which clarify defined boundary between the fatigue and residual zones. In contrast, the 60 T6 alloy was characteristic by a less distance boundary between these zones and the presence of cleavage structure. Fifth, in the case of the 66 T6 treat alloy, or for the 60 T6 treat alloy, a similar element of fracture surface was observed. The fatigue surface has a plastic character, but is greater and much more information for 60 T64 aluminum alloy. The irregularity of the surface in the form of numerous peaks of 60 T6 alloy transfer to lower plasticity and higher brittleness. And on the end, the surface of the fracture looks different for the 63 T6 alloys. In this case, the fracture surface is characteristic by numerous of various size, void of large and irregular cracks. The surface structure indicates the sudden detachment of material fragments under impact bend. Thank you for your attention.